slides?
Yes, sir, we can see the slides.
Okay. Okay. So we will continue our discussion with exploration seismology as we have been doing yesterday. So we said in the whole exploration workflow in the oil and gas industry, the seismic uh, workflow essentially sits here, where you capture access up after you capture the primary areas, then you acquire seismic data, and then you process your seismic data and ultimately interpret that seismic data based on to get out some geological information from it. So we will see how seismic acquisition is done. We will briefly see how processing is done, and we will focus on some of the interpretation aspect, what we exactly see in a seismic line. Okay. But remember, here the source is, of course, um, is anthropogenic, is man-made, right? So there is no natural earthquake. It's the earthquake created by human being. Okay. So this is the basic concept that would clear what happens in reflection seismology. Now, this is the energy source. So you can think this one to be analogous to the focus of an earthquake. So there is an explosion. So the explosion can be done in different ways. It can be done, with the means of a dynamite, or it can be done with the means of a very strong hammer. I mean, hammer, it's just the name is hammer. I mean, it's no way it looks like a hammer that you are familiar with. It's like a big pillar of solid steel which actually thumps on the ground. Okay. So the idea is, whether you do it with a dynamite or whether you do it with that hammer, what you do is you create some sort of elastic energy. So you create some sort of sound waves, and that happens generally like 2 to 3 feet below the ground. So they make like a hole, and within that hole, such energy is generated. Okay. And then, of course, as a result of that elastic collision, the elastic waves start to propagate, right? Now, you can see here with the blue dotted line, the wave front is drawn, and then a particular ray path is also drawn. Okay. Now that wave is essentially propagating down, and as soon as it hits the boundary between the blue layer, sorry, the green layer, my apologies, the yellow layer and the orange layer, as soon as it hits the boundary, some part of the energy is actually reflected back to the ground. And then if you have a seismometer installed here, okay, you receive that signal. But some part of the energy is penetrating inside, and then it founds again a boundary between the orange layer and I don't know what is the name of this color, greenish orange, maybe, yeah, or grayish orange. In this particular layer, when it finds that boundary, the same thing happens. Some part of the energy goes inside, and some part of the energy is reflected back, of course, right? Now, what these boundaries are, they are they could be lithological boundaries. I mean, but the fundamental boundary that this sort of elastic wave propagation sees is essentially boundary between different acoustic impedances. And we defined what acoustic impedance is. Acoustic impedance is nothing but the product between the density of a particular layer and the velocity of the elastic wave through that layer. Okay. So if the rho 1 V1 is different than rho 2 V2, then it would uh, see that transition being a boundary. Okay. And then it will act accordingly depending on their contrast of acoustic impedance. Okay. So if the contrast is less, of course, most of the energy will be transmitted, very little will be reflected. If the contrast is high, then most of the energy will be reflected, very little will be transmitted. I hope you understand that. And if there is no difference, of course, it acoustically they are like the same layer, and then the whole energy will be essentially transmitted. Now, so let's
So in the reflected rays, so they also won't get again like successively reflected and
yeah, yeah, absolutely, absolutely. They do get reflected again. Okay, so in this boundary again, they get reflected. Some part of it gets reflected, and some part of it gets transmitted. Yeah, absolutely. So it exactly follows the way optics work. Okay, so now nothing different than that. Now let us imagine that at this point I have
Excuse
a
me,
size. Yeah,
excuse me, sir.
yeah.
Over
Go ahead.
over here, how do we find out the wave front which we have to choose to determine the velocity of the wave?
No, the velocity of the wave is not a function of the wavefront by itself, right? So wavefronts are everywhere. There is a wavefront here, there is a wavefront here, there is a wavefront here. I'm just looking at the ray which is incident at an angle, maybe I here. Okay? So there will be another ray which is perpendicular. There will be another ray which is going at a there is another ray path which is going at a parallel to the bed. So everything is there. I'm just focusing to understand the concept only on this ray path. Okay. So the rays are in all the
Uh,
directions, of course. Because the wavefront, it's like when you make a pound, the all the energy is deep. I mean, going in all the possible directions, right? Okay. Just to understand the concept, we are concentrating on this particular ray path. That's about it. Is that okay?
yes, sir.
Okay. So now let us say that at this point and at this point there are two devices. Devices means listening devices, as they say. These are two of your seismometers. Okay. Now seismometer one and seismometer two. Now, for example, after the explosion, after the explosion, the wave, the ray goes, the elastic wave hits the first boundary and comes back to device one after zero point 0.4 second. Okay. Now this zero point 0.4 second has a very fancy name, which we call as two-way time. Okay. Let me just take a snip. Just a moment. Hang on. Let me open up my whiteboard. Again, this problem, man. Okay, let me just take a snip. This is a PDF presentation. This is not a presentation which is. All right. Now we are in business. Okay. So after the explosion is done here, the wave essentially propagates like this, and then it comes back here. The time that it takes, which is, this is my device 1, D1, and this is my device 2, D2. The time it took is around 0.4 second. Okay. And then at D2, I observe another, the ray essentially goes here, gets reflected at the second boundary, comes back to D2 after zero point 0.8 seconds. So this zero point 0.4 second or 0.8 second, this is what we call as TWT, or two-way time. Okay, two-way time. Why it is called two-way time? Because it actually, accounts for the path traveled by the ray to go down and then come back. Okay, so to go down and to come back. Okay. Now remember, there are all sorts of waves are going right now. Okay, and you will understand that in a bit, in a moment. Just focus on these two waves for the time need to understand the concept. Then we will try and see a actual scenario how how all the waves will actually interact with these two devices, right? So now you have got a, 0.4 second two-way time, and you have got a 0.8 second two-way time. Now, so at device 1, so at device 1, you can see that at 0.4 second, I am observing the arrival of the first wave. Okay, I am observing the arrival of the first wave at 0.4 second, and at device 2, I am observing the arrival of the wave at 0.8 second. Now you see how this particular, now this, the representation that you see here is called a wave trace. Okay, this particular representation is called a wave trace. Yeah, or it has a very fine name as well, which is also called wiggle. Now if we try to read this data, yeah, what is this essentially? What is this data? Okay, so you can see it looks like a sine curve. Okay, and it has an amplitude, of course, and it has also a phase. Okay, so this is essentially measuring the ground motion. Okay, the ground motion that is happening due to the arrival of the wave. Okay, and then of course it has a positive part. Positive part means the compressional part, and then an immediate negative part. So this is the compressional part, and this is the dilational part. So this is one phase, of course. This is phase 1, and this is, of course, phase 2. Right? Different color is phase 2. So this is called a wave trace or a wiggle, and that has actually three components. One is its arrival time, of course, the time at which it arrives, and then it has another two components, of course. So whether it has phase, whether we are observing the compressional phase first, or whether we are observing the extensional phase or dilational phase first, that is another thing. And then it, of course, has an amplitude. Okay, the amplitude could be small, the amplitude could be small, or the amplitude could be large. Okay, Small amplitude means the energy which has come back to the device is less. Okay? If the amplitude is less, then that means the energy that has come back to the device is less. And of course, if the amplitude is more, that means the uh, energy that has come back to the device is more. Now let's go back again and try to look at this figure. Okay. Now, say for example, so we said that the reflection will be essentially guided by V1 rho 1 and V2 rho 2. The contrast between V1 rho 1 and V2 and rho 2. Okay. If the contrast is higher, if the contrast is higher, so that means, say for example, that the acoustic impedance is increasing with depth. Let's see, that's one of the most common thing that happens in nature. Although there are exceptions that happens, but generally what we observe that V1 rho 1 is actually less than V2 rho 2 is less than V3 rho 3. Okay, that means the acoustic impedance generally increases with depth. Okay, now that is not always the case, there are exceptions, but this is more or less that happens in nature. Okay, now let us say that there is a very large contrast between layer 1 and layer 2. Okay, so a large contrast means contrast in terms of acoustic impedance. Okay, so the condition is V2 rho 2 is highly greater than V1 rho 1. Okay, this is the situation we are thinking of. So what would happen that in this boundary, most of the energy will be actually reflected back. Okay, most of the energy will be reflected back, and little energy will be actually transmitted. Okay, so as a result, the device D1 will also observe a stronger amplitude. Okay, observe a stronger amplitude. But if that would have not been the case, then I would have observed, perhaps if the contrast would have not been that strong, then I would have observed perhaps a less amplitude in my wiggle. Okay, is that clear? Is that clear for you, what I have discussed so far?
Yes,
Okay.
sir.
Excellent. Now let's go ahead and see. So we will let's just keep this discussion hold for a moment, and we will come back to this again. So we defined wiggles, we defined wave trace. Okay. Now, how seismic acquisition is done? Okay. So a 3D design, a 3D survey design is based on imaging objectives. Say, for example, the image area, which area you want to actually do your seismic surveys on, the target depth, whether your reservoir is sitting at 3,000 meters, whether your reservoir is sitting at, 5,000 meters, that is something which will uh, determine as well what sort of seismic survey you want to do. The depths of the beds, the velocity of the subsurface, the elastic wave velocity, the size and thickness of the bodies to be imaged. Okay, so these are all the things that matters how a seismic survey should be designed. I know for now it is not making much sense to you, but remember these points. But we will see as we go ahead with the lecture. You will see that how these all points are important, right? Now, survey parameters, survey area, fold, offset, sampling, shooting direction, etc. I'll explain what fold is, what offset is, what sampling, shooting direction. I will explain that in a moment. Okay. And then balance between data quality and this is dollar. Okay. So that means if you want to get a better data, of course you have to spend more money, right? Now there is, of course, there is a balance. I mean, you should not spend so much that you completely go out of business, right? So there is, you have to come to an optimum choice that you get optimum data quality, as well as you are not spending a lot of money. So these are the few things on which a 3D survey, which is done for a seismic campaign, are based on. Okay. Now, this is what happens in a land operations, and you can see the operations where seismic surveys are done are huge, extremely expensive. Companies after companies has been built upon doing seismic surveys. Okay. Now, the seismic surveys are not only important in oil and gas industries. For example, you want to create a nuclear reactor. Okay. Want to create a nuclear reactor, you want to create a nuclear disposal site, and then you have to know also about your subsurface. Okay, so in those cases as well, seismic surveys are hugely helpful. And as I was telling you, that there are companies after companies which have been built and have made fortune building seismic companies, and the operations that are done in oil industry is no less than sending a rocket in moon or in the Mars. Okay, or so the it's equally complicated. It's equally scientific, technical, as well as expensive. Okay, so and also the people required to run these operations are also huge. So this is what is happening in a land operation. So you can see here these trucks. Okay, and some of these trucks you will observe that there is this like a uh, mm, this is the hammer that I was talking about. This is the hammer that I was talking about. So there is like a pulley, there is a piston which actually helps this huge, this you know heavy base to actually pound over the ground. So as you pound over the ground, and these are called vibrators. Okay, that disturbs, that creates the disturbance or the elastic collision. And then the detectors that I was talking about are the geophones, where you actually detect, which are nothing but seismometers as well. Okay, the fancy name here is geophones. The geophones that actually listens to the sound, that means observes the devices that I was talking about, the listening devices. Okay, now, of course, land operations is really, really expensive and really, really time consuming, very complicated. Okay. Sometimes instead of these hammers, you also use dynamite, as I was talking about. Okay. Now, if the territory is completely flat, it's easier to do a seismic survey. But if the territory is, of course, mountainous, okay, or it is within a city, it becomes fairly difficult. I mean, if you are pounding these things, these can create like 3 magnitude earthquake or so. Okay. So you don't want that to happen in your neighborhood, right? Because of course it will create a shake in your house, and you don't want that, right? So if it is like a desert area, okay, it's a blazing to do a seismic survey inland. But then, of course, if it is a mountain, you can imagine you have to pull all these trucks up, you know, and then you have to find a way to pound them equally on the ground. It becomes fairly complicated. I mean, you don't want to only restrict your survey on the roads, right? So you have to go in the mountains itself to do such surveys, right? So it becomes fairly complicated, and hence more expensive as well. So on the other hand, the marine operations are bit simpler. So what they have essentially is like a boat, and they are generally called vessels. Okay, write down the name. They are called vessels. The boats which are used for seismic survey are called vessels. And then at the end of the vessel, there is something called a air gun. So air gun does the same thing like it is done by the vibrators in land. That also creates some sort of acoustic disturbance on the water itself, and it pounds on the ground, and it creates energy, and that energy actually penetrates through the subsurface, and then it is actually listened by these these chain of hydrophones. Okay, there's chains of hydrophones. As you can see here with this board, there are like streams, so they are like strings on which there are uh, hydrophones are attached to these strings. Okay, and these are called fishes. Okay, so you can see there are four fishes, four streams here, and maybe in one stream there are like 10 hydrophones. Okay, I have spent quite a lot of time in these boats. Okay, and can be quite boring sometimes because you spend like 20, 50, 20, 30 days in a boat and keep on taking such data. Can be boring, but initially it's very challenging and interesting as well. So what you do in these air guns, you actually make the sound, and in these um, hydrophones, you receive the signal. Okay? So now you think, suppose, let me just, this is little bit annoying, but let's just try to make the best of it. Suppose this is the area you want to, uh, this is the area. Suppose this is the area you want to do a survey. Okay. This is the map view. You are looking from the top. So what you essentially do, that you take your boat. So this is your boat, and then there are four streams, of course. So you take your boat like this, then you take your boats like this, take your boat like this, and then do perpendicular to it. So this is how the boat is moving, okay? And while it is moving, it is collecting data, collecting data. So what I have got, that I have got subsurface information along these lines. Okay, now if I look at it once more, I am getting my subsurface information along these lines. Okay, so annoying. I am getting my subsurface information along these lines. What sort of information I'm going to talk about in a moment. Now, of course, these places are empty. We don't have any data in, right? So what do? I essentially interpolate the data. Okay, I interpolate the data. So these individual traces are called 2D seismic data. And when we interpolate and actually form a data cube, when we interpolate and form a data cube, okay, that is what we call 3D seismic data. Okay. Now, if we take the 3D seismic data, maybe I take it in 1990, and then I take another data at 2000 after 10 years. And within that 10 years, maybe that particular oil and gas field has been producing oil and gas. Okay. So we see that due to the change in fluid content in the subsurface, the seismic responds differently. Okay. So now I have taken a 3D at 1990 and I have taken another 3D at 2000. Okay. So then we compare these two seismic, one taken at 1990, one taken at 2000. Okay. And that sort of survey is called 4D seismic. 4D be simply because so there is 3 dimension, of course, and then 4D means we are applying time into it. Okay. This is nothing but 3D surveys done in 2 times. Okay. Now you can imagine moving a boat along this line is rather easy. Okay. But then moving your trucks and going everywhere and pounding in the ground and getting data out is rather difficult, especially if the terrain is hostile. Okay, if the terrain is not very friendly or flat, then it can be very difficult to create a survey pattern like I have drawn here. Okay, so hence land seismic acquisition is more complicated, more time consuming, more technical, and more expensive. Okay, but the offshore, I mean, in the sea, the seismic acquisition is rather easier. Okay, now of course you know that the example that I have drawn, that if I increase the number of 2D lines, if I increase the number of 2D lines, I have to interpolate less. The more 2D lines I increase, I will get a better data in 3D. Okay. But then increasing more 2D lines means that I am making my project more expensive, right? So I have to find a balance whether how many 2D lines I want to take. Okay. So these 2D lines are called inlines, and then the perpendicular ones are called cross lines. Inlines and cross lines. So how many inlines and how many cross lines do I want to take to actually get an optimum 3D data, to generate an optimum 3D data, so that I kind of optimize the data quality as well as the cost. But remember, if I increase more 2D lines, of course, I have to interpolate less. If I have to interpolate less, that means my uh, data will be better, but then it's going to be more expensive. Okay. So is that clear how the acquisition is done, more or less, from for land and sea for you guys? Did you understand?
So in a 3D survey, we also try to find out what at like what depth the earthquakes originate and all that as well.
No, it's not about originating earthquakes. Okay, it's not about, it has nothing to do with earthquakes. These size surveys are done to image the subsurface, how the subsurface looks, how the layers are, whether there are any faults, whether there are any folds, so on and so forth. Okay, that's your first question. And second thing is, it doesn't matter whether it is 2D or 3D. In everything you get a depth. Okay, so 2D seismic line means it doesn't have, I mean, it's just a line, it's just a section of the subsurface. It's not the whole volume of the subsurface. Okay, now if you put so many sections together and then you interpolate in between, you should be able to create a 3D volume from your 2D seismic. Is that clear?
So like we stack the 2D data over each other and like compare in 3D.
It's not exactly stacking. So because you cannot stack, because they are geophysically at different places, right? You don't stack them. You have the data, then you interpolate. You use some sort of algorithm like kriging, convergent interpolation. There are many data interpolation algorithms, right? So use data interpolation algorithm to actually know what is in between. Okay, so what is a simple algorithm? What is a simple interpolation? I know, for example, any data, right? Suppose I have 3 cells. I know this is 1, this is 3. What is most likely the value of this one be? This one, the in between cell?
2.
2. How do you know that?
Interpreted.
This is called interpolation, because I have observed 1, I have observed 3, and then I kind of do some sort of algorithm to find out the data in between will be 2. Okay, but you don't know whether it is 2.5 or 2.75 or 1.85. You don't know that, right? Understand my point? Now, for
Yes.
example, here the same area I divide it into 6 thing, right? Then I get here 1.1, 1.4, yeah, 3, 2.75. Then I can actually interpolate the value of this unknown cell better, simply because I have more data point, right? It's actually guessing the unknown by knowing the data of the surroundings. That is what we define as interpolation, right? Exactly the interpolation you do here. You know how the subsurface looks here. I know how the subsurface looks here, but I don't know how the subsurface looks here. So I kind of interpolate.
So this is in 2D.
All these lines are in 2D. You know, these lines, if you take this line, how this line would look like? This line would look like this, where this is X, this is Y, and this is Z. And then, of course, there is a subsurface structure inscribed into it in all these lines, right? But then
Yes.
I don't know something which is in between. So they are all 2D. This is a 2D line. A trace is this is a 2D line, and then to create 3D, you interpolate these 2D lines.
Okay.
Okay, it has a depth component, but remember, it has nothing to do with studying earthquakes. You don't study earthquakes with reflection seismology.
Okay.
This is to image the subsurface. Okay, how the subsurface looks. Any other question? All right, let's proceed then. So this is the seismic acquisition part, okay? And I hope you understood a little bit. I mean, it will be more clearer as we go ahead. Now, we have just seen, so this is how a raw seismic data looks like. Okay? This is a raw 2D seismic data, how it looks like. Okay. So what we have seen here, you can see that I have these devices, and then I have got these traces. I have got these seismic traces. Okay. So then what would happen? Let's try to draw something for you here. Okay, now. Let's say this is source. Let's source, I am calling it as S. Let us say we call it S1, D1, D2, and then I'm drawing it here. Okay. Suppose I have another another device here. Let us say that is, let's say this is D3, this is D2. Okay. So now let us say I have another wave coming up here. I'm sorry, I should have drawn it in a. Let's wait for a moment. Okay. So now I am just trying to target this particular interface. Okay. Now this is D1, this is D2, this is D3, this is S1. So at D1 for this particular interface, I get a wiggle. At D2, whether that, so this is my two-way time, okay? So at D2, whether you tell me whether the trace for the same, at D2, whether the trace for the same reflector will be at a higher TWT or at a lower TWT. Tell me that. Huh? Whether it will be at a higher TWT, whether I should place this, I have to place the wiggle for this reflector as well, right? So whether this wiggle at D2 for this particular reflector, whether it will be down or it will be up. Tell me. Whether it will take more time or less time.
It will take more time.
Take more time. Simple. They will have more or less similar amplitude, huh? Although I could not draw it properly, but they will have similar, more or less similar amplitude. And for D3, then again, like this. So similarly, for this reflector as well, let's make another color. It is deeper, so that means it will start eventually from deeper place. Now imagine I have, 100 such, not even 100, maybe I have 500 such interfaces. Okay, so I will get 500, such series of wiggles, right? 500 such series of wiggles representing all these layers. Now what I can do, I can essentially add these, sorry, essentially add these to get a length versus two-way time picture. Okay? So that is what exactly you are looking in here. Okay. So these, if you are looking them closely in a computer, zoom them in, what you would have seen that all these, like they have been doing this, right? They have been doing their kind of slanted, right? They're kind of slanted. And that essentially speaks for these are these individual wiggle sets. Okay. So here is my source, and these are all my individual detector locations, okay, for a particular 2D line. And that is exactly what you are seeing here. Now, the data the data which comes from the devices that are close to the data which comes from the devices which are close to the source are called near offset data. The data which comes from the detectors that are close to the source are called near offset data. The data that comes from the further part of the source, they are called far offset data. Okay, so near offset, far offset. Remember why they are important, I will explain later on. Okay, so the data that comes from the detectors which are closer to the source, we call them near offset. The ones which are away, that we call far offset. Now, if we only work with the data which is from near offset, that data is called near stack data. Okay, so here is my source. Okay, and then D1, D2, D3, and there are maybe 50 DN. Okay, D30, D50, DN. Okay. Now, if this part of the data, yeah, is near offset, this part of the data is got far offset. If I only work with the data of the near offset, that data is called near stack. If I only work with the far offset data, that is called far stack. If I work with the full coverage of the data, that is called full stack. Okay, and why, we will see why they are important in a moment. Okay, so far so good, clear? बताओ यार, क्योंकि ये डिफिकल्ट कॉन्सेप्ट है तो समझने में दिक्कत होता है. क्लियर है अभी तक?
Yes, sir.
ओके, चलो. अभी क्या है? Now you have seen that these reflectors. So now, by the way, if I join them, if I join these wiggles, the lines that we get, okay, are called reflectors. Okay? If we join these wiggles, the lines that we get are called reflectors. Now you can see that these reflectors are, of course, are slanted. Okay? Now the example where we have started working with that, those layers although were horizontal, right? So if I now look at this one, we go here, sorry, we go here, this is where we have started. The subsurface lithology is more or less horizontal, right? It can be dipping, but in this particular case, they are more or less horizontal. But then the trace that we have created, the seismic trace that we have created, they are all slanted, right? They have a dip. So now what I have to do, I have to essentially, from this raw data that I have created by shooting seismic, I have to take it through a process which we call data processing and create the image of the subsurface, where the individual attitude of all the beds will be perfectly put into place. Okay, all the images, all the right attitude of all the layers will be put into place. Okay, from here we have to go here, and the process by which we go through this is called data processing, which we will cover in tomorrow's pre-recorded lecture. But you can see here, Here, if I look at this particular picture, of course, I cannot make anything out of it, right? It's almost unclear. I don't know what is the subsurface lithology. But if I look here, I can see a lot of things, right? You can observe that these layers are slightly folded. Can you tell me what is this layer? What does this layer indicate? If you can tell me what is this layer, what does this layer geologically indicate, I will be extremely happy with you. Can you tell me?
Sir, moho.
नहीं यार, मोहो नहीं. मोहो तो बहुत नीचे है. ये कहाँ? ये तो 3-4 किलोमीटर का डेटा है. मे बी दिस इज
Conrad discontinuity.
डिसकंटिन्यूटी नहीं यार, ये अनकॉन्फॉर्मिटी है. This is an unconformity. Why it is an unconformity? You can see the attitude of the beds, overlying beds is not the same as the underlying beds. So this is an unconformity. This is an erosional surface, right? This is an erosional surface. Now you can see, observe, this is a fault. So what does that mean? That this layer and this layer were together, okay, before the deformation. And then, of course, there was some sort of disturbance that happened, and then this layer kind of got displaced here. So it created a fault. So when that fault was created, there was perhaps an earthquake. But that was in the geological past, which we are not interested in this particular case. Here we are interested to know whether I can locate an area where I have oil and gas. Okay. For that particular purpose, I need to see how the subsurface looks like. Okay. So these are the individual layers. Individual layers here means, what does this mean that this layer is different from this layer? What does this mean acoustically? Can someone tell me? We talked about it. Two different layers means what? What is different for them?
So density.
Their acoustic impedance, not only density, also the velocity of the wave. Their acoustic impedance is different. Okay. V rho, the product of V and rho, that is different. So why this reflector is very, very bright and why this reflector is little dull? Can you tell me? What did we say? When the brighter deflector means higher amplitude. Brighter deflector means higher amplitude. When do I have higher amplitude?
So that layer is more closer to us.
No, that has reflected more energy. When does it reflect more energy? When does it reflect more energy? When the acoustic impedance contrast is more. So that means the overlying layer and this layer has more acoustic impedance contrast than something which is dimmer. If the layer is dimmer, if the layer is coming up to you as a dim layer, that means the amplitude is less. Okay. And if the amplitude is less, what does it mean? That the reflected energy is less. And when is the reflected energy less? When between two layers, the contrast of the acoustic impedance is less. Is that clear? Tell me.
Yes, sir.
है ना? तो जहां पे आपको दिखेगा कि यहाँ पे देखो डल दिख रहा है ना, उतना ज्यादा ब्राइट नहीं है. ब्राइट नहीं है मतलब क्या है? इसका एम्पलीट्यूड कम है. एम्पलीट्यूड कम कब होता है? जब साइस्मिक एनर्जी, रिफ्लेक्टेड साइस्मिक एनर्जी लेस होता है. रिफ्लेक्टेड एनर्जी, साइस्मिक एनर्जी लेस कब होता है? जब दोनों लेयर के बीच में एक्वास्टिक इंपीडेंस का कॉन्ट्रास्ट कम होता है. ठीक है. So tomorrow what we will see how we can actually transform this particular picture to something which looks more geological, and the process which we take it through is called data processing. Okay. अभी बताओ कोई क्वेश्चन है तो. you have any question. Is there anyone who doesn't understand Hindi? Sorry, I spoke in Hindi for 2-3 lines or some lines. If it is, just tell me. There was a funny incident that happened when I joined ISAR Bhopal. I think 2016, first batch I was teaching, and I was showing them copies, and one of the students did not do very well, and I, you know, uh, in a sweet language, I perhaps scolded him for 10 minutes. Why did you not do well? Why it was not clear to you and everything in Hindi. And after 10 minutes, he replied, "Sir, I don't understand Hindi." So, and then I did not have enough energy to again communicate the same in English. So, I laughed and stopped. Anyway, I hope it's not the case for you. If it is, please raise your hand. I mean, that's no problem. And, we will not speak in Hindi. Anyone having any doubts? आदिल, श्रीवत्स, राहुल, निरुल, बताओ यार, कोई डाउट है अभी तक? क्योंकि इट्स गोइंग टू गेट बिट मोर कॉम्प्लिकेटेड इन प्रोसेसिंग. इस पे कोई डाउट हो तो फिर प्रॉब्लम है. प्रीति, साइमा, प्रकृति, ओम, बताओ. डू यू हैव एनी डाउट?
Sir,
हाँ. Yes, Adil.
wiggle, wiggles and reflectors, they are different, right?
When you stack the wiggles together, it becomes a reflector.
Okay, sir.
Okay? Wiggle is an individual trace at a particular detector, and then when you put all the wiggles, we will see that in the processing. When you put all the wiggles together, of different detectors, it becomes a reflector. Okay.
Yes, sir. So
Anything
that
else? Yeah.
colored map that we got in that reflectors were shown.
They are reflectors. Yeah, they are reflectors because now if you zoom them in, I mean, if you go too much into zoom, it will come as individual wiggles, because it's the wiggles that you put together to create your reflector, right?
Yes, sir.
So the blue color, conventionally, the blue color speaks for the positive amplitude, and the red color speaks for the negative amplitude. Okay, I mean the plus side of the phase and the minus side of the phase. Okay. That's the general convention.
Okay, sir.
Anything else? I can tell you seismic is the most practiced geophysics in the world. Okay. So that is so the students who study geophysics for 5 years, of course, you are studying it only for one semester, that for one course, but there are students around India and all over the world who study geophysics for the whole year. And seismic, they spend maybe at least 5 to 6 courses, right? So it's very huge. And the gravity one semester, something like that. So it's and we are trying to put everything together in a single semester, because that's the only you get to learn geochemistry in many different uh, phases of your syllabus. But unfortunately for geophysics, it's not the case. Our courses are not designed in that way. So this is the only part of only opportunity in structural geology. Of course, you will learn a lot of mechanics, stress, strain, those sort of things, but not exactly these things. I mean, you will do a little bit of interpretation of seismic, but this is the only chance that you have got to study geophysics, which is equally important. And then yeah, so I try to give you flavors of everything, even if I can't get into the depth of it because of the time constraints, as you know. I'll try to give you the flavor of everything that is there. Okay. Now, if you want to develop, you can develop it by yourself. Okay. Any other questions? Else, I'll just stop the class today, and I will give the pre-recorded lecture. But I'm going to send you the quiz questionnaire now, and whatever I have taught, is good enough. It will contain mostly magnetism and seismic, and then I want it to be submitted by today 6 o'clock. Okay. All right, then I will stop the class here. Thank you.